Hello, this is Benoit Tournadre from the French National Center for Meteorological Research. So I will present you some work we are doing for the Ocean and Sea Ice Satellite Application Facility, OSISAF, and so work we are doing on Meteosat Second Generation SEVIRI sensor to estimate sea surface temperature. So there is already a OSISAF operational data sets of sea surface temperature, but here we want to make a reprocessing. So to study a long-term time series of sea surface temperature, the operational scheme has some limits, notably because we are using different versions of the relative transfer model Ltda. There are also near real-time data inputs like cloud mask that is from nowcasting, a satellite application facility, the a priori information on sea surface temperature that comes from OSIA analysis, or else weather data on humidity and temperature profiles that is from IFS forecasts. So all this, for the reprocessing, we want to replace it by the best data that we can use. So for weather fields, for atmospheric fields, we use ERA5 analysis. We will use a single version of Ltda, which is the most version operational, the version 13. For cloud mask, we use the class 3 data from the CMSAF, so a climate data record of cloud mask. And for the a priori sea surface temperature, we use the climate data record of ESA CCI in its analysis form. So Meteosat Second Generation SEVIRI, it's a geostationary sensor. So it has the ability, compared to ESA CCI, to give us information on the dial variability of sea surface temperature. So this is an information that can be used for validating the diurnal cycle of SST in models, also to correct them, and it can also be assimilated into analysis or reanalysis like OSIA or ERA5. So that was for the presentation. I also, for the reprocessed SST product, we are using reprocessed satellite imagery from SEVIRI. So which means for now mainly updated calibration for infrared channels. So it's not exactly a fundamental climate data record. It's just updated calibration. There are plans to make a fundamental climate data record from SEVIRI, but it will be later, in some time after the reprocessing is made. So also the reprocessing compared to the operational algorithm, it will be for us the opportunity to make an updated method. So until now we were using a nonlinear SST algorithm with Ltda relative transfer adjustment. But here we want to apply the bias-aware optimal estimation that is described in the paper Merchant et al. 2020. So in the equation that you can see of the bias aware of the optimal estimation, we will try to retrieve the variable Z that contains sea surface temperature and water vapor total column. So the idea is that these are the two variables that contains the most information to describe the brightness temperature observed by the SEVIRI thermal infrared channels. So to estimate them jointly, we need a priori information that comes from sea surface temperature a priori ESA CCI sea surface temperature analysis, so the climate data record recently published this year, and water vapor from ERA5 that we use as total column for the day. And so the idea is that the second term will adjust the sea surface temperature and total column of water vapor to get the most consistency between the observation of brightness temperature Y by SEVIRI compared to the simulations of brightness temperature F of XA, which is a Rtitov simulation for state vector XA containing the temperature and humidity profile and sea surface temperature of the studied condition. So to make the link between this difference of brightness temperature and the SST and column of water vapor, we need a gain that is given by this term in front of the brightness temperature, and that will translate the brightness temperature into a correction of SST and water vapor. So it contains the variable k, that is the both matrices of sensitivity of brightness temperature relative to the SST and to the water vapor, so that you can see on the two plots below here and there. And we also need the error covariance matrices S epsilon and SA, so that are respectively containing the error due to observation and the error for SA on the a priori profile, a priori state vectors. So to estimate S epsilon SA in normal optimal estimation, it's only depending on the expertise you have on a priori information and satellite data. But in bias-aware optimal estimation, it will be adjusted taking into account the buoy observation of SST that you consider as a reference dataset. So the bias-aware part of optimal estimation is useful for that, and also to adjust to correct the bias that you have on the a priori profile of on the a priori information on SST and on column of water vapor, and also on your simulation of satellite brightness temperature. So all this will be implemented on the European weather cloud. So it's something that we are exploring currently. It's the first activity we are making for OSISAF on it. The interest for us to use the EWC is that some data, input data like ERA5 or Cloud Mask Class 3 may already be present on the cloud by other users that can share this data, so we don't need to make an extra download of it. Another point is that for processing 20 years of data, so it requires a lot of computing resources, and there are possibilities on the cloud to use shared computing resource with other users via what we call the batch processing with the software HT Condor. So we are beginning these tools. If you want more information, you will be welcome to contact us and more broadly on the reprocessing activities. So thank you.